Chapter 10 Human Alteration of the Atmosphere. Section 10.7 Stratospheric Ozone Depletion. So, within the Earth's atmosphere is a zone where ozone molecules are concentrated, and we call this zone the ozone layer. The ozone layer sits at an altitude of about 10 to 50 kilometers, with a maximum concentration at about 25 kilometers. So here we see the distribution of concentration of ozone within the atmosphere, and the ozone layer is from essentially 10 kilometers to about 50 kilometers, with, as I said, a maximum occurring at approximately 25 kilometers. There is also ozone at the Earth's surface. That ozone is created from a variety of different industrial and human activity type processes. The ozone layer naturally shields living things on the Earth from ultraviolet radiation. So the sun's ultraviolet radiation can be harmful. It can have a number of negative effects. Over the last few decades, scientists have measured a seasonal, now it doesn't occur all year long, just in particular seasons, a seasonal thinning of the ozone layer, and it's primarily occurred at the South Pole, and it's been given the name the ozone hole. A smaller decrease does occur at the North Pole, but it's much smaller in scale. A severe decrease in the concentration of ozone could lead to the following negative effects. It could increase the formation of cataracts in the eyes of organisms. It could lead to greater sunburning of skin tissues. It could increase the incidence of skin cancer. Ultraviolet radiation can destroy the acids in DNA, causing mutations. Higher ultraviolet radiation levels cause a suppression of the immune system of organisms. It would adversely affect crop growth and, of course, animals due to some of the effects already described. Higher UV radiation levels would cause reduction in the growth of phytoplankton in the oceans. And finally, it could have a climatic effect. It could cause the cooling of the stratosphere, and therefore that may lead to some sort of feedback mechanism to the climate that occurs near the Earth's surface. Now, ozone is created naturally in the stratosphere by combining atomic oxygen, so single atom of oxygen with molecular oxygen. Most of this occurs in the subtropics and tropics, and this process is run by sunlight. You need sunlight for this to occur. As I said, most of it's created at the tropics and subtropics, and then redistributed by atmospheric currents high up in the atmosphere to the middle and higher latitudes. Ozone is also naturally destroyed by sunlight, but in particular by absorption of ultraviolet bands of sunlight. Ozone can also be destroyed by just the simple collision of ozone with other atoms and molecules in the atmosphere. Since the late 1970s, stratospheric ozone amounts over Antarctica during spring, from September to November, have decreased by as much as 70%. So a hole develops, it lasts for a number of weeks, and then it fills back in. So the following images of the South Pole show the increase in the size of this hole. So what we're looking at is the maximum size of it in 1997, 1982, 86, 1990, 94, 98. So we can see how it's becoming much larger and a greater concentration of ozone is being destroyed. 2002, 2006, and 2010. This animation shows the change in ozone concentrations, the minimum values, between 1979 and 2013. And the scale on the side shows the concentration of ozone. So blue and purple are low concentrations, as in the previous graph shown. So scientists wondered what was causing this depletion. What was the agent? And it turned out it was an artificial chemical humans produce for a number of reasons. CFCs, chlorofluorocarbons. They were originally created back in the early 20th century by GM for a replacement for ammonia, which was used in refrigeration units. CFCs have also been used as a propellant in spray cans, cleaner for electronics. They can be used to sterilize hospital equipment and to produce styrofoam bubbles in cups. CFCs are long-lasting complex molecules, lasting up to 200 years. By 1988, some 320,000 metric tons of CFCs were used worldwide. So when CFCs are released to the environment, they slowly drift in the atmosphere up into the stratosphere, where UV solar radiation causes them to be decomposed chemically, and this releases chlorine. It's the chlorine that reacts with the ozone molecules, converting them into oxygen molecules. Now this reaction is a little bit more complex than just what was described. This reaction also requires a source of nitrogen. And over Antarctica, you can get clouds that aren't composed of water vapor, but frozen nitrogen. These clouds are called polar stratospheric clouds. The nitrogen in these polar stratospheric clouds acts as a catalyst and prolongs the reactive life of chlorine by a huge quantity. A single chlorine atom can remove about 100,000 ozone molecules. But as I said, these polar stratospheric clouds are composed of nitrogen, and in order for nitrogen to freeze, it has to be very, very cold. Temperatures need to be in the less than minus 85 degrees Celsius. And for this reason, this is why it's more common over Antarctica. The upper atmosphere in the Arctic doesn't get to minus 85 degrees Celsius as easily as the air above Antarctica. So Antarctica has these cold temperatures, and it's the primary place where this ozone depletion is occurring. We don't get temperatures that cold in the middle latitudes or in the lower latitudes. It has to be over Antarctica. So the United Nations got the states of the world together to consider this problem. And there was a meeting in 1987 called the Montreal Protocol. So scientists helped politicians formulate a global plan to reduce CFCs and to stop the damage that was going on to the ozone layer. This plan has been amended, has been altered in 1990, 1991, 92, 93, 95, 97, and 1999 to quicken the schedule of production and consumption reductions. By 2009, all countries belonging to the United Nations were participating in the protocol. Although some research suggests someone still is using CFCs because they are measuring new emissions of these chemicals globally. The culprit might be China. The Montreal Protocol called for a 100% reduction in the creation and use of CFCs by January 1st, 1996 in the world's more developed countries. Less developed countries had until July 1st, 2010. So has it worked? Well, here there's many different forms of CFCs. Here are the two most common, CFC12 and CFC11. And these are measurements of the concentration of these two types of CFCs in the atmosphere. And you can see that for CFC11, its concentration in the upper atmosphere started decreasing just before 1995. For CFC12, it's a little bit later. The decrease in CFC12 started in about 2002, 2003. Here's a short video of a scientist talking about the recovery of the ozone hole over Antarctica.
The Montreal Protocol has been a great success at banning the production of ozone-depleting substances. And we know this because we've been measuring those substances at the Earth's surface since the 1980s or even before in some cases. So before the Montreal Protocol, ozone-depleting substances at the surface were going up rapidly. Once the protocol was signed and the regulations went into effect, we saw at the surface levels of ozone-depleting substances going down, and so that's great. But those substances have to get up into the stratosphere before they can destroy ozone, and they have to break down high up in the stratosphere, and the chlorine that gets released from the chlorofluorocarbons, that's what actually destroys ozone. What we haven't had up until now is any measurement inside the Antarctic ozone hole that the chlorine levels there is actually going down. What I've shown is that if you're very careful about when you measure hydrogen chloride, that's HCl, in the atmosphere, and you measure it over time, you can see that HCl, so that reactive chlorine that destroys ozone, those levels are actually going down inside the Antarctic ozone hole. So that's great. So that's part of saying, hey, the ozone hole's recovering, it's getting smaller, and it's because of declining chlorine. But the other part is to also look at how much ozone depletion is going on at the same time, because ozone levels can vary for a lot of different reasons, mostly because of temperature. If one year it's warm, you don't have as much ozone depletion. One year it's really cold, you have more ozone depletion. So it makes it really hard to see the signal that the atmosphere is showing us this is the ozone hole really recovering. So what we did in this study, we were able to look at ozone changes during a period of time in the winter when most of that ozone change is coming just from chemical changes, so that temperatures aren't really affecting it very much. And we're able to do this because of measurements from the NASA Aura instrument called the Microwave Limb Sounder. So what we've seen by using the MLS data is that ozone depletion has declined. It does vary a lot still, but it declines, and it's declining sort of in step with the chlorine changes. And so that's what we're excited about, is that we see for the first time chlorine levels are definitely going down, and ozone levels are responding to it.